you have a point A and a point B in a gravitational field of the Earth. And and the point A is higher than the point B, connected by a path, and there's a point mass with mass m sliding down this path without friction. This path could be a parabola, or it could be a polynomial function of third degree or of nth degree. It could also be a logarithmic function. The only condition is that the path never goes higher than a. Otherwise, due to conservation of energy, the point mass would stop sliding. So now we would like to find the time, a general expression for the time of such a point mass sliding down. And this is quite amazing because it could be really any path, and you can calculate the exact time without friction of this point mass sliding down in a few quite easy steps. So first of all, we need to find the expression for the time. We know that the velocity per definition is ds over dt. From there follows that dt equals ds over v, and from definition of integral, the definition of the integral, we know that that the integral of dt equals t. So that means we take the integral on this equation, so that means t equals the integral of ds over v. Okay, now that's already quite good. We have an expression for the time, but we need to now find ds and v. So now, what is ds? Thanks to our good friend Pythagoras, we know that ds equals dx squared plus dy squared, and the root of that. So in this problem, you could imagine that there's a coordinate system here, x, y. And this problem is placed in this Cartesian coordinate system. Okay, but we want to change this a little bit to make it nicer. So we factor out dx squared. So that means we have 1 plus dy squared over dx squared, and in brackets times dx squared. Okay, and now we see that dy squared over dx squared, let's write this down, dy squared over dx squared is the same as dy over dx all squared, which is equal to y prime squared. And in this expression above, we can take dx squared out of the root, so it becomes dx. So ds equals the root of 1 plus y prime squared, I don't need the bracket anymore, times dx. Perfect, we have an expression for ds. Now we need an expression for v. So what is v? From the conservation of energy, we know that the potential energy is equal to the kinetic energy, and the potential energy is mgh, but h in our case is y, is equal to a half mv squared. And from here, m cancels, and when we solve for the velocity, we get 2gy and the root of that. Perfect, we have an expression for the displacement and for the velocity. Now, now we insert these two expressions into our original equation for the time. Let me write this down again. Time equals the integral of ds over v. So that means the time is equal to the integral of 1 plus y prime squared times dx over the root of 2gy. This can also be written like this, 1 plus y prime squared over 2gy and dx. And this reminds us of our typical integral with the dx at the end. And maybe to make it look nice, we can take out the constants. So that would be 2g. So time equals 1 over root of 2g, because they are, of course, constant, times the integral of 1 plus y prime squared over y root over that times dx. So this is our expression for the time.